On this problem, we're talking about a coin being flipped 10 times. We're trying to find the probability of getting exactly 5 heads. So I'm assuming a fair coin here. And I'm counting the number of heads, so I have repeated trials. It's the same probability each time I do a trial, and I'm counting the number of heads, which means I have a binomial distribution here. We're counting the number of heads, so that's going to be my success. You'll notice whenever I'm starting a binomial distribution, it's a very good idea to define what a success is, because it's not always immediately evident. In this case, I'm counting heads, so it makes sense to define that as my success. But if I'm counting heads in one part of the problem and counting tails on the other part of the problem, I might want to change. I might want to just take that into account, because otherwise I might just get confused. Alright, so success is getting heads. N, the number of trials, is 10 because we're flipping the coin 10 times. The probability of getting a heads on each individual flip is 0.5 or 50%, or 1/2, however you want to write that. And we're saying the probability of getting exactly 5 heads. That means we're saying exactly 5 successes. So this is binomial PDF 10.55. Now, if we wanted to find the probability of getting at least 2 heads, this is a little bit of a different problem, because our n and our p are still the same. N is 10 and p is still 0.5, because we're still flipping a coin, and we're still flipping it 10 times. But again, if we think about the number of different outcomes we could get, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the number of different number of heads we could get. We're saying the probability of getting at least 2 heads. That's talking about all of that probability. And so if I'm using the complement rule like I did on that previous example, I want to figure out, well, the probability of getting 1 or fewer head. I would actually have to do 2 separate calculations to figure this out. The probability that x is less than or equal to 1, and this is the probability that x is greater than or equal to 2. Because we're trying to find the probability that x is greater than or equal to 2, that we get at least 2 heads. So I could do this in one of 2 ways. I could say 1 minus the binomial PDF of, let's see, there's 10 trials with probability of success 0.5, and I'm talking about 0 successes. I'm going to put these in parentheses. Actually, let's make those brackets. Plus the binomial PDF of 10, 0.5, 1. So I'm running through this binomial PDF binomial PDF function twice. Once for the probability of getting exactly 0 heads, and once for the probability of getting exactly 1 head. So let's go ahead and type that into the calculator. 1 minus parentheses. Let's do binomial PDF 10.50. I'm going to add that to the binomial PDF 10.51. Close up my 2 parentheses. One of them was a bracket when I was writing on the paper, or on my whiteboard. Add those together, and we get 0.989 approximately. And this actually does agree with our intuition. We're quite likely to get at least 2 heads when we're flipping a coin 10 times, because the complement is the probability we get, or the event we get exactly 0 heads or exactly 1 head. Each of those are very unlikely events. I could actually figure out what the probability of getting exactly 0 heads or the probability of exactly 1 head. I could do those independently, add that together. I'm just a fan of plugging it all in together like this, because I think it shows a better example of where all the numbers are coming from. And it also prevents me from wanting to round in the middle of a problem.